Today we want to talk about the curl of a vector field, like how to calculate it, and try to get a sense of what it represents, and then see how that fits in the context of our fundamental theorem of calculus for vector calculus. So fundamental theorem of calculus, vector calculus edition. So the structure of the fundamental theorem of calculus is that we integrate a derivative over a set by evaluating the function at the boundary of the set. So the integral from a to b of f prime of x dx is f at b minus f at a. A and b is are the boundary, form the boundary of the interval from a to b. F prime is the derivative of the function f. In vector calculus, we have a new thing taking the role of the derivative, and that would be the del operator. This is a vector made up of partial derivatives. It's not so much that we're going to be multiplying by the partial with respect to x. We're going to be finding the partial with respect to x. We're going to be performing that operation, and that's going to be our kind of multiplication when we get to dot product. We can take the del operator, apply it to a scalar function, and come up with a vector. That vector is called the gradient. And that showed up in our fundamental theorem of calculus for line integrals. So we have the gradient, which is del f. And then since the del operator is a vector, we can use the del operator in a cross product and a dot product. In this case, we're not going to be applying it to a scalar function. We're going to be applying it to a vector function or a vector field. So del cross f is the curl of the vector field f, and del dot f is the divergence of the vector field f. Yesterday, we talked about the divergence of the vector field, del dot f, and we thought of that as the amount of expansion or compression. It's the expansion of a gas. And it makes sense in the fundamental theorem of calculus as we look at all the points in a solid or in a three-dimensional space. If we look at the expansion of the gas at every point in that solid, we can calculate the vector field as it flows through the surface, the boundary of the solid. So if we think about what's going on in Stokes' theorem, where we integrate the curl of the vector field over some surface, we can calculate this by looking at the vector field, by calculating a line integral of the vector field around the boundary of the surface. So let's look at the curl, del cross f. Make a calculation to remind ourselves the form of the curl is a vector. And then think about what this could represent in the context of the fundamental theorem of calculus. Let's start off with a calculation. Let's take a vector field. Do I have one? No, of course not. Let's grab a vector field. We'll have x squared y. Actually, let's write down what we're going to do first, and then do the example. So the curl of a vector field is going to be del cross f. We're finding a cross product of the del operator and the vector field. So let's be specific about what the vector field will look like. There'll be a scalar function of x, y, and z for the I component. There'll be some other scalar function for the j component, and a third scalar function for the k component. So notice that F1, F2, and F3, those are all scalar functions that are the components of the vector field F. So if I want the cross product of the del operator and the vector field F, I find the determinant where of the 3x3 matrix with I, J, and K across the first row. The second row will be the components of the del operator, so partial with respect to x, partial with respect to y, and partial with respect to z. And then the third row will be the components of the vector field F. So F1, F2, and F3. So we're going to calculate this cross product by calculating this determinant, and we're going to use cofactor expansion across the first row, mostly because we want this to be in terms of I, J, and K. We can do this expansion across any row we want, but then the I, J's, and K's will be all over the place, and we have to gather them all up. Since we want a vector with an I, J, and K component, let's just do cofactor expansion over the first row. So we're going to do cofactor expansion across the first row. So I'm going to have the I component. We're going to have the I component times the determinant of its cofactor. So if I take out the first row and the first column, the cofactor will be partial with respect to y, partial with respect to z, F2, and F3. Because we're doing a determinant and we started in the upper left, the first row, first column, we're going to go to the first row, second column. We alternate signs in calculating a determinant. So we're going to subtract. And then we're going to write the cofactor for by taking out the j column. And that's going to be partial x, partial z, F1, F3. So it'll be partial x. I'm going to abbreviate. And there's our j component. Then we're alternating signs, so I'll switch back to plus and write the cofactor for the first row, third column, which will be partial x, partial y, F1, F2. And once again, I'm going to abbreviate to conserve vertical space. So now we'll find the components, I, J, and K by calculating these determinants. Normally we would multiply A, B minus B, C. We're just going to do our normal determinant stuff. A, B minus B, C. Normal determinant of a 2x2 of A, B, C, D is AD minus BC. But in this case, since A and B aren't just numbers or functions, instead of multiplying, we're performing the operation. So we're going to take the derivative. Instead of saying dy times F3, we're taking the partial of F3 with respect to y. So instead of multiplication, we're performing the operation. So I have partial of F3 with respect to y. Minus the partial of F2 with respect to z. There's our I component. minus our next cofactor, partial of f3 with respect to x, minus the partial of f1 with respect to z. And finally, partial of f2 with respect to x, minus the partial of f1 with respect to y. So here is how we find the curl of the vector field F. Partial of F3 with respect to y minus the partial of F2 with respect to z. That's going to be our I component. Our j component will be the partial of F3 with respect to x minus the partial of F1 with respect to z. And then for our k component, the partial of F2 with respect to x minus the partial of F1 with respect to y. The way I like to remember these parts is to make associations. I, x, and F1, j, y, F2, a, z, F3. Those are the things that go together. Notice that the component of I in the term in the curl has I is associated with x and F1. Those are the two things that do not appear in the I component. The I component is all concerned about what's going on with F2 and F3 and with the Y and the Z. Furthermore, we have to mix we mix the F2 and F3 with the Y and a Z, but they never match up with the column. That's not how, we don't do one thing with itself, with its column mate. So we start with F3 with respect to Y minus F2 with respect to Z. So it's always mixed. The component doesn't have any of its column mates, and the partial derivatives are never with their column mates. So in the J component, we're going to have, since J has the Y and F2, we're not going to use Y and F2 in that determinant. We're going to use F1 and F3, and we're going to use X and Z. But they're not going to be with each other. They're going to be mixed up. So the partial of F3 with respect to X minus the partial of F1 with respect to Z, mixed. And then the same thing happens in K. K is associated with Z and F3. So the component of K is not going to use those. We're going to use X and Y, and we're going to use 1 and 2. And the partial derivatives are always mixed. Partial of F2 with respect to X minus the partial of F1 with respect to Y. Remembering it this way, we always just make the bigger F go first. So I have F2 minus F3 minus F2, then F3 minus F1, then F2 minus F1. Now, this is the way that I normally write the curl, where the J component is negative. To remind myself that this came from 3x3 determinants, alternating the signs. And this helps me remember what order the functions need to go in. Just remember where the derivative, helps me remember where the derivatives are. But you might look at this J term and say, I hate that the J term is negative. We should multiply by the negative. And so this is a more common way to see the J term expressed is by changing the sign and then changing the order. So it is very common to see the curl expressed with a positive J term, but then the order doesn't match in my mind. This looks super hard to remember just to have all the components be positive. This is just some kind of psychological damage that has been inflicted upon me. I don't know when. I don't want to inflict that psychological damage on you, so I want to say, this is how I write the curl, and this is how it's more commonly written. So I want to acknowledge, even though I don't like this blue J term, I prefer this way to remember it. I realize that I am the weird one in this scenario. So I don't know how you're going to get along with either of these. Only you can decide that. Actually, for the most part, you're not deciding certain things like this. You're finding out what works, and then that's just going to be what works for you. You don't get to decide how your brain works. Your brain just works how it works, and then you learn how to work with it. You know what I mean? I wish I could be normal and just remember the curl this way, with this blue J term, but I can't, so I won't. You know what I mean? This is not to endorse the concept of learning style. Learning style has been shown to be not true. So if you're walking around with the idea that you're a particular kind of learner, that's not true. Yeah, that was made up. That was one of those things that was a hypothesis that everybody kind of ran. Then we started testing the hypothesis, and I'm like, wait, this doesn't work at all. This is not how it works at all. They're like, it's out in the world. We believe it. George Washington had wooden teeth. Now we all believe that now. It's just true now. Sorry. Yes. You know what I mean? It's like headlines. It's like there's like a bunch of stuff that we always tell ourselves, and we usually tell ourselves by telling everybody else. Right? Like one of my favorite things now. Oh, I don't care what people think about me. Like, if you actually didn't care about what people thought about you, you wouldn't have to feel the need to go around telling people that you don't care what they think about you. You absolutely care that they think about you. You want them to think that you don't care what they think about you. That's part of your brand. You're like, well, I am an independent thinker, and I think just like all these other independent thinkers. This is people just trying to come up with their own brand. You know what I mean? Anyway, that was all stalling so that you could write this down and see all the patterns that we have to help us remember. I always look for stuff like this mostly because I've been teaching trig for the last couple of semesters, and then you get to the identities, and you have to see how they're all connected. You can't just remember each individual trig identity in and of itself. That's like trying to learn the words to a song by memorizing each line individually. You have to know how they go together. You have to get the connections between the lines so that you don't stall at the end of the one line you memorized. You got to have the whole thing, the whole plate. I don't think this will be too much of a disaster. We'll just go with x squared y I plus zj plus xyzk. And let's find the curl of f. So we're going to need to put together all these partial derivatives. We're not going to want to fill this out actually, maybe you do. I shouldn't say we're not going to want, because maybe you're going to want. Let's just list the parts that we need and try to put them together in the way that we know that the curl is put together. So I've got these three functions. I've got f1, F1 is my I component. So F1 is x squared y. Our F2 is just z. And F3 is xyz. So these are our individual components. We know we need partial derivatives of each of these three components. We need two of the partial derivatives, not all three. And let's remind ourselves of which ones we need. F3 with respect to y and F3 with respect to x. F2 with respect to z and F2 with respect to x. F1 with respect to z and F1 with respect to y. So if we think about what's grouped together, I need the partial derivatives that aren't vacuum. So F1 doesn't need the partial with respect to x. I need the partial of F1 with respect to y, and I need the partial of F1 with respect to z. So partial of F1 with respect to y is going to be x squared. And the partial of F1 with respect to z is going to be 0. There are three partial derivatives, but I only need two of them. Let's find the 6 partials we need. So for F2, I don't need with respect to y because that's all in the same column. I need with respect to x and with respect to z. For F3, F3 is in the column with z, so I don't need the partial with respect to z. I need the partial with respect to x and the partial with respect to y. So with respect to x, we get yz, and with respect to y, we get xz. And now we have to remember how this gets put together. We know that for the I component, I'm not going to need anything in the red column because the red column has the F1 stuff in it. F1 is in the same column as I, so I need the other two. Which other two do we need? We need the ones that don't involve x because x is in the column with I. We don't need any partial with respect to x because those are in the columns with I. So I don't need these two. I need these two. And if I'm going to keep my j term negative and not do that weird blue make it positive thing because everything has to be positive, cheer up. Everything is great. We're going to go with F3 part with respect to y minus F2 with respect to z. Those are the two that show up. 3 with y, 2z. That's what shows up in the I. So F3 with respect to y, xz, minus F2 with respect to z, 1. That's our I component. I'm still kind of doing that determinant thing. The x stuff and the F1 stuff, that's in the column with I, so it's not going to show up in the determinant. Then we'll move on to the j term. And I'm going to do subtraction because that's psychologically what I feel the need to do. Now, in the j term, I'm going to take out anything in the green column. I don't need any of this green stuff because that's the stuff that's in the column. That's with F2, and F2 is in the column with j. So also, I don't want any of the partials with respect to y. So I'm taking out this column. And I don't want any of the partials with respect to y because partial with respect to y is in the j column. So I don't want xz and x squared. I want yz and 0. So I'm going to have yz minus 0. And then for the K component, K is in the column with F3, so I don't want any of the F3 stuff. I just want the F1 and F2 stuff. Furthermore, since K is in the partial with respect to Z column, I don't want partials with respect to Z. I want the X and the Y. So I'm going to go F2 with respect to X minus F1 with respect to Y. And there's my K component. This has some terms that are zero. And those terms that are zero means we've got some extra parentheses running around. So let's clean this up a little bit. So we'll have xz minus 1 for an I component. Now a little messy. Minus yz in the j component, and minus x squared for a k component. So here we have calculated the curl of a vector field. So what could the curl represent? Why did we call it curl? How is it going to show up? So things we know. It's a cross product. So we know that curl is a vector that is normal or perpendicular to this del operator, whatever that means, because it's an operator, and the vector field F. So this is a vector that is perpendicular to the del operator and the vector field. So just thinking about what the cross product represents. We got to be thinking about the curl. So is a cross product so it's perpendicular to the del operator and the vector field. This raises an interesting question. What does it mean to be perpendicular to the del operator? What's orthogonal to the del operator? Perpendicular to the vector field, that we can imagine. Even if, so the vector field is pointed in one direction. Clearly, this curl is going to have to be perpendicular to that. It's still a cross product, so it's perpendicular to the two vectors and uses the right-hand rule. So we point in our fingers in the direction of the first vector. So we point our fingers in the direction of the operator. Man, that's still weird. I still don't like it. And we curl our fingers towards the vector field. And our thumb will be pointing in the direction of the vector. We have to do it this way because if we change the order of the cross product, we know we get the opposite. So remember, the right-hand rule is if we've got two vectors, so if I write u cross v, I put my fingers on u and curl them towards v. And so the vector will be coming out of the page. There's u cross v. But if I do v cross u, it'll be pointed the opposite direction. So if I put my fingers in the direction of v and curl them the short way towards u, then now will be pointed in the opposite direction. When we talk about the angle between the vectors, we talk about the short way, not the 360 minus theta. So as weird as it is to think about, we put our fingers in the direction of the operator, whatever that means, and we curl them towards the vector field. So here's what we're measuring. What we're measuring is how much the vector field is swirling around. Our curl is kind of representing how much the vector field is curving around. If our vector field is very gently curving around, measured by its partial derivatives, then we're going to have a small amount of curl. But if it's really tightly wound, then we're going to have a larger amount of curl. Remember that the vector field is the magnitude times the magnitude times the sine of the angle between them for the cross product. So the magnitude of, oh, and then there's a dot product. So I didn't say all the things that I need to say. So what we want to think about is how much, this is telling us how much the vector field is curled around, how tightly wound the vector field is. We want to think about how tightly wound the vector field is. Imagine a whirlpool, and if you're far away from where the whirlpool is pulling everything in, not much curl, kind of like making these big sweeping arcs around. As you get closer to where the whirlpool pulls you down under the water, you're getting more and more curl. Think about more curl near the middle of the whirlpool. how spinny is the vector field. Let's imagine a surface and the boundary of that surface, the surface S and the boundary of that surface. So the curl shows up in Stokes' theorem. It says the integral over S of the curl of a vector field dot dA. How spinny the vector field is at any given point at all the points on the surface is the vector field around the boundary, a line integral around the boundary of the surface. So the surface integral of the curl of the vector field is showing us how spinny the vector field is at all the points on the surface. And Stokes' theorem says that we can measure this just by looking at the vector field around the boundary of the surface. Remember the rule for how C is the boundary of S. We've got some surface. And around it is the path C, and it is oriented in such a way that the region or the surface is on the left as we go around. This is just our way of saying it's counterclockwise, but it's not a circle, so saying counterclockwise is a little bit weird. So we say C is the path oriented according to the right-hand rule. So the left side of Stokes' theorem says, let's just add up how curly the vector field is at all the points on the surface. And Stokes' theorem on the other side says you can calculate that by just looking at the vector field going around the path, integrating the vector field around the path that surrounds the surface. Just like in the divergence theorem, we look at how the gas is expanding at every point inside the solid by looking at how the vector field is going through the surface. That's the boundary. We integrate a derivative over a set by evaluating the function at the boundary of the set. Any questions? Clearly, we're just playing to get an intuitive idea because I said how swirly is the vector field at every point on the surface, and swirly is not an actual math term. So if you're like filling out some answers on some test for some professor that isn't me, don't be like, oh, well, we're measuring how swirly the vector field is. And then that professor will be like, oh, excuse me, did you say swirly? At which point you should just sell me out. It's like, oh yeah, and he's just like, oh, it's how swirly it is. And then I'll get the email. And they'll be like, oh, are you telling students how swirly stuff is? I'm like, oh yeah, because it's swirly. I would have called it the swirl of the vector field, not the curl of the vector field. That's all boring. I'm just kidding. I would not do that exactly. Yeah. Yeah, the Stokes theorem has the form of a fundamental theorem of calculus. And so we're integrating a derivative over a set by evaluating the function at the boundary of the set. We're integrating the derivative over a set by evaluating the function at the boundary of the set. That's our fundamental theorem of calculus. That's the form, the structure of the fundamental theorem of calculus. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day. Thanks for playing. See you Thursday.